Hey everybody, this is Intro to Electrical Circuits, and hopefully you guys find this helpful. Okay, so Intro to Electrical Circuits. This is just kind of a brief overview. I just want to give you guys a sense of something that's, kind of applicable to real life. So we're going to talk about some electrical terms, talk about electrical power, and electrical components, and what a circuit looks like. So the worst thing about me not being there in person is you're going to miss all of my electrical jokes. So here you go. Here's this one, which kind of sums up a lot of my electrical jokes. Okay, first thing you need to know about electricity in a circuit is what is potential difference. Okay, potential difference. Well, potential difference is the electrical potential between two different locations. So what the source is and how much it is across different electrical devices, that difference is what we call the potential difference. And what it really is it's the voltage change between 2 points on a circuit. The biggest change being your power source, so either a battery or some other electrical device supplying the power. So that's going to be where your biggest voltage increase is going to be. And the total potential difference in a circuit is the voltage supply of the battery or the power source. So if you've got a 12-volt battery, that is the total amount of voltage that you're going to have for that circuit. Each of the devices will use some of that voltage, but that's that. And like I said, it's measured in volts. So the symbol is V for voltage. We measure that in volts. I like to use the analogy of water because it kind of helps, make the connection kind of make sense in your head. So if you think of the voltage source as the water pump, it's what's pumping out the water into the circuit. It's what's applying all of the current. All the electrons are being pumped out. So that's your potential difference. That's your source. And like I said, we measure the potential difference as voltage. The next thing is current. Current kind of makes sense. If you think of current as water flowing, it's the current of the river, how much water is flowing through the river. So in an electrical sense, it is the rate of electrical charges flowing in the circuit. We measure the current in amps. The symbol is I. I have no idea why, but we measure current in amps, and the symbol is I. An amp is the flow of 1 coulomb of electrical charge every second. Don't worry about what that means. Just know that it's 1 coulomb of charge every second. So an amp is the flow of 1 coulomb of electrical charge every second. If we'd done some of the electrical demonstrations, you would have gotten to see how that worked, but just know that's what it is. And the net amount of charge that passes through a wire's full cross-section per unit of time. I know that sounds weird. Just know that it's the amount of charge, which we call Q, and we measure that in coulombs, divided by the amount of time that passes. Okay, the next thing is electrical resistance. And electrical resistance is kind of just that. It is what is resisting the flow of electrical charge through the system. Every single device in a circuit has some kind of resistance. Obviously, things like metal have very little resistance. Other things have a lot of resistance. That's why you wear rubber gloves when you're working on electricity, or you use plastic screwdrivers when you're doing electricity, because they don't conduct electricity very well. They have a lot of resistance. If you think of resistance, and we're talking about water, is like obstructions in the water, things that are slowing down that flow of water, that would be kind of resistance. And this is just a silly thing. It kind of helps remember what it is. R is for resistance, and we measure it in ohms. So if that helps you, great. But R is for resistance, and it's this funky horseshoe shape is the units, and what that is ohms. All right. So this brings us to what is a circuit? Well, a circuit is a closed path that allows electrical charges to flow from a source and then return to that source. You may have done simple circuits back in middle school, looking up little things. If we'd been in class, we would have gotten to play with some of this. I'm going to show you a simulation, and if you want to play with it, you can play with it, but I'm going to show you some stuff. So just to cover a couple of the devices that you might see. This is in your book, so you don't necessarily have to write them all down, but if you want to. So the squiggly line is what we call a resistor. Any straight lines are wires. A battery is these two lines, two parallel lines next to each other. Traditionally, the longer side is the positive side, the shorter side is the negative. Switches are important to know. That's what cuts the flow of electrical flow in a circuit. Diodes, don't worry about the diodes. We're not going to talk about diodes. And then light bulb, some kind of device that has to be doing something. For our simple circuits, we're just going to be worrying about light bulbs, but it could be anything. It could be your TV, it could be a motor, a fan, any kind of little device that's in your circuit. But for us, we're just going to talk about light bulbs. So here is a very basic circuit. You have your power source here with these two parallel panels. The convention for current flow is always from the positive side to the negative side. So in this situation, it would be going around clockwise, and that's the flow of the current. Now, if you want to be specific, actually the electrons are actually flowing the opposite direction, but the convention has always been positive to negative, so that's what we tend to stick with. So we have our three things. We have voltage, current, and resistance, and we need some way to connect all those. So this is contributed as Ohm's law, and it simply states that the voltage is equal to the current times the resistance. And that voltage is equal to the current times resistance is the same. That rule, that equation can be applied to any specific device or to the whole circuit as a whole. And you'll see that as we do some examples. So here's one example. So the potential difference of 240 volts, so like a battery, is applied to a 150 ohm resistor. How much current flows through the resistor? Well, if we list out our knowns, we have our voltage, we have our resistance, and we're looking for current. So we use our super duper difficult equation, plug everything in, and solve for current, and we get 0.16 amps. So a couple of these that I want you to try. So go ahead and try this one. Pause if you need to. Hopefully you came up with something around 155 volts as your answer for that. Then I have a second one for you. So when a potential difference of 18 volts is applied to a wire and the wire is conducting 0.35 amps, what is the resistance of that wire? Hopefully you got 51 ohms. All right, so I'm going to show you a simulation. All right, hopefully you can see my simulation. I will put a link to this simulation up on the thing. So if you want to get into it and play around with it and see how it works, you can do that. So I've got my circuit set up here. I got my light bulb and I got my battery and I have my switch. And if I close my switch, then I get my current flowing from the positive side through my circuit all the way back to the negative side, and then it goes back. And if I check out the values of things that are going on, I have 9 volts of electricity, or 9 volts from my battery flowing through, and I've got 10 ohms for my light bulb. And if we wanted to measure the current, we can measure the current in our circuit, and as you might expect, it'd be 0.9. And like I said, you can play with this, you can put all kinds of different resistors and stuff in there and see what it does, but that is your basic circuit. Okay, so that leads us into what power is. And if you remember power from before, back when we talked about energy, remember power is, oh, I've got it down here. Power is work over time. So it's how much work gets done over how much time it takes to do it. Well, in electricity, the way we measure it is the current times the voltage. And that gives you how many watts of power you are supplying to your circuit. It's still a joule per second. You can still figure out how much energy is being used if you know the time, because remember, change in energy is the amount of work that you do. And I have more electricity puns for you. All right, so let's do a quick little thing. So a handheld fan operates on a 3-volt battery. If the power generated by the fan is 2.2 watts, what is the current supplied by the battery? Well, if we use our equation, we plug in our power and our voltage, then we can solve for our current. All right, so once you give this one a try, see what you get. Hopefully you ended up with 9 watts. All you had to do was multiply the 12 volts and 8.75 amps together. Okay, so I already posted the 2 worksheets up on Google Classroom, so do those for homework, and I will post the solutions probably on Thursday or Friday. Hope that helped, and we'll talk to you later.